Let's dive into multiple regression. That's just a regression that takes more than one variable into account, more than one feature. The concept is actually pretty simple. It's just answering the question, what if I have more than one variable influencing the thing that I'm trying to predict? So basically, I'm doing a regression that I don't just have one feature that I'm measuring to try to predict some value. I have many features that might come together. So for an example, that might be predicting the price of a car based on its many attributes. The car has a lot of different things you can measure that might influence its price, such as its mileage, its age, how many cylinders it has, how many doors it has, things like that. And you can actually take all of those into account and roll that into one big model that has many variables as part of it. Now, as often is the case in data science, there is some confusing terminology here. In addition to multiple regression, which is using multiple features to predict a single value, we also have the concept of multivariate regression. And you would think that would mean the same thing, but it doesn't. Typically, when we talk about multivariate regression, we're talking about not only having multiple feature attributes that we're trying to use to make a prediction, but we're also trying to predict more than one thing at the same time. So maybe I'm trying to predict not only the price of a car based on its mileage and age and number of doors, I'm also trying to predict how long it will take to sell it or something like that. That would be an example of multivariate regression, where we have multiple things we're trying to predict in addition to multiple features being used to make those predictions. Either way, though, the way we do it is actually pretty simple. So we can just have, instead of a single coefficient attached to some single feature variable, we can have multiple terms with multiple variables. So we can say that we can predict the value price based on some constant value alpha times some coefficient called beta 1 times your first feature, which, say, could be mileage, plus some coefficient beta 2, which might be multiplying with some other feature like the age of the car, plus beta 3 times the number of doors, whatever you want to do. And those coefficients are just measuring how important each factor is to the actual end result. Now, this assumes that all of your features are normalized going into it, so you can actually compare those coefficients together fairly. If they're not normalized, that coefficient will also be working to scale that feature into the final result as well, and that can also be informative. If you actually work out the values of beta 1, beta 2, beta 3, and whatever else you might have, that can also tell you a little bit about what features are actually important for your model. So if you end up with a very low coefficient for a given feature after things are normalized, that might be nature's way of telling you that that feature isn't actually very important for predicting the thing that you're trying to predict. And that can help you to simplify your model by eliminating feature data that you don't need, so that's a very useful thing. That's called feature selection, and it's often a very important part of building a good machine learning model. Now, all of this still uses least squares, so in our notebook we're going to use something called OLS. That stands for ordinary least squares, and it can handle multiple features like this. So we can still measure the fit of this thing overall using R squared, nothing is different there. And another thing that we need to point out is that this whole thing assumes that there's no dependency between these different features. Notice that I'm treating all these features independently with their own coefficients. So if there is in fact a relationship between these features, this model will not capture that. And this is actually an example of where that would probably be the case. For example, the mileage on a car would probably be highly correlated to the age of the car, and this model will not capture that relationship. In fact, you'll probably be just fine just using mileage or age independent of each other, but this could at least tell you which one of those is more important to keep. So with that, let's dive in and actually fire up a notebook and see how it works. There is something called the stats model package that makes things easy, and it offers the OLS model that we can just use to go off and make it chug away and do it all for us. So let's make that example of multiple regression real. Go ahead and open up the multiple regression notebook file here, and you should be seeing something like this. All right, let's see multiple regression in action. Fortunately, the stats model package has an OLS regression model that can handle multiple regression. It's pretty easy to use, although there are a few quirks that we'll talk about here that you need to know about. What we're going to try to do is predict car prices using multiple regression on various attributes of the cars. For example, the mileage, the number of cylinders, and the number of doors. And I do have a real data set for you here to play with that I've uploaded to our website. So the first thing we're going to do is import pandas and call its read Excel function to load up this Excel spreadsheet of a bunch of data about cars and their attributes and what they sold for. And we're going to load that up into a data frame called df. So let's go ahead and shift enter to do that. Now, if you get a failure there, just try it again. Sometimes accessing the internet from a notebook can be a little bit unreliable, but usually if you just try it again, things will cache up and it will work the second time. All right, so let's try to visualize this data. The first thing you usually want to do when you're dealing with a new data set is to inspect the data. Make sure that you can be comfortable with it and manipulate it and get information out of it, and make sure that it's what you expect. So that's all we're going to do in this next block. We're going to load up matplotlib so we can plot things. We'll import the numpy package so we can manipulate our data. And we will create a new df1 data frame that just extracts the mileage and price features from our original data frame, from that Excel spreadsheet that we loaded up as df. So now all we're going to try to do is see, is there a relationship between mileage and price? You would think there would be, right? You would think that higher mileage cars in general would cost less than low mileage cars. So let's see if that's true. Let's bucket this up. So we're going to create a bins data frame, and we're going to call np.arange. What this is going to do is break up our data into 10,000 mile chunks between 0 and 50,000 miles. Got it? So this is going to give me back a range of data between 0 and 10,000 miles, 10,000 and 20,000 miles, all the way up to 50,000 miles. And then we will create this groups and take that mileage and price feature data, group it by those bins that we created, and compute the mean for each one of those bins. So now groups is going to contain the mean price for each one of those ranges of mileages. We'll print that out, make sure that it looks reasonable, and then we'll plot it and see what we got. So let's hit Shift-Enter. And you can see here that we do have those ranges we expected. So between 0 and 10,000 miles, the mean mileage was $55.88 and the mean price was $24,000. Work your way up to 30 to 40,000 miles and the mean price drops down to 19,463 miles. And if you plot it, then you see what you expect. Higher mileage cars in general cost less than low mileage cars. Now, I will warn you, there are some outliers in this data set, and this might not hold true all the way up beyond 50,000 miles. So maybe there's some like collectible sports cars that have high mileage, but they're still worth a lot, right? So this data set's actually a good one to play with for dealing with outliers too, if you want to dig into that. And I'll encourage you to do so at the end of this exercise. So anyway, our objective there was just to make sure that we're comfortable with the data, we're able to load it, we're able to manipulate it. So far, so good. All right, so let's build a model. So we're going to start by importing statsmodel.api as SM. So this is going to be importing the model that we're actually going to be using here. We're going to import standard scalar from sklearn.preprocessing, and we're going to create a new instance of standard scalar called scale. Standard scalar is what we're going to use to normalize all of our feature data so that they're all in the same general range. That makes models work a lot better in some cases, including this one. So let's start by extracting the feature data that we want. We're going to go back to our original data frame that was loaded directly from that Excel spreadsheet and just extract three features: mileage, number of cylinders, and number of doors. And by convention, we call our feature array X, uppercase X. So we're going to try to build a model that only tries to predict price based on mileage, number of cylinders, and number of doors. Now, there's actually a lot of other data there in the source data. And for example, the make and model of the car, that would be pretty important as well, you would think. But this sort of regression model, you can't really mix and match ordinal data with numerical data, so we kind of have to pick one or the other. In this case, we're going to go with some numerical features, and that's why we're omitting things like make and model of the car. By convention, lowercase y is our labels, the things that we're trying to predict. In our case, that is the price, okay? Now we need to pre-process that feature data to make it work well with our model. This is a pretty common thing to do. So we're going to call scale, which is our standard scalar, fit transform, and pass in that mileage, cylinder, and doors features from our X array, extract the values from that, pass it into fit transform, and that will give us back scaled mileage, cylinders, and doors that have been scaled down into a normal distribution. So more or less, a bell curve between -1 and 1. And we'll stick that right back into the original X array in the same columns that we started with. So this line, again, is going to scale the mileage, cylinder, and doors features within that data set into a bell curve between -1 and 1, into a normal distribution. This next line is kind of a quirk of OLS. So you'll remember from the lecture that there is a B0 term, a constant y-intercept for each for where we start from. And unless you add a constant column to your feature data, the model can't create that. So in order to allow it to have a y-intercept, to have that B0 constant in the model, we need to call statsmodel.addConstant and pass in our feature array there. All that does is add a column full of ones to the beginning of our data frame. We'll print that out and make sure that it looks as we expect, and then we'll actually train the model itself. And that's a one-liner here. We just call statsmodel.ols, pass in our label data, pass in our feature data, and call fit to fit that data to our model and create a new estimator. We will then print out summary information about how that training went, and it will tell us, it will give us some insights about what's actually going on inside the model right there. So let's shift enter and kick that off pretty quick. All right, so the first thing we printed out was that feature array that's been scaled down, and you can see that we have that constant column that we stuck in the front there. That's going to be used for modeling the y-intercept of the model, B0. And you can see that our feature data has been scaled, more or less into plus or minus -1 range into a normal distribution. So looks like that worked. We then trained the model and printed out summary information about the trained model. And by looking at this, you can get some insights. R squared and all the usual metrics here are here for you to look at. You really got to read the documentation on what these stats really mean, because they're not always what you expect. For example, R squared is based on a weighted metric that is not what you would normally think of as being R squared, but they're still comparable, as you're running different models on the same data. Let's take a look at the actual coefficients here. So this is kind of like the meat of the output of our model here. These are the actual coefficients for those B0, B1, B2, B3 terms in our multiple regression model. So you can see our constant term is actually pretty big. $21,340-ish is our y-intercept. Mileage actually has a negative coefficient. So again, that makes sense because as you increase the mileage, the price would decrease. We're also seeing the cylinders have a really big impact on it. So the number of cylinders in the car actually seems to be the highest absolute magnitude of coefficient that we see here. So rather surprisingly, the number of cylinders seems to affect the model more than anything. I wouldn't have seen that coming, but I guess it makes sense. If you have really high cylinder vehicles, you're probably in the world of like exotic supercars, right? So this might be driven by outliers where somebody has some, $1 million supercar with 10 cylinders, and that might be skewing this whole model off and doing weird things. So again, outliers are something to dig into, and we'll talk about that more later. Number of doors, surprisingly, also a negative coefficient. The number of doors, more doors does not mean more money, it turns out. And if you think about that again, sports cars, sports coupes, they tend to be two-door, and they tend to be expensive. So a little bit of an interesting insight in the data just from looking at these coefficients and nothing more. All right, moving on. So this was actually a pretty convoluted and complex way of figuring out that more doors does not mean more money. And I want to reiterate that you always want to go for the more simple solution when you can. So I could have figured that out with one line of code here much more simply. If I just grouped my data by the number of doors and computed the mean price for each set of door numbers, let's see what we come up with. So right there, I can just see with that one simple line of code without building a big fancy machine learning model that the mean price of a two-door vehicle is $23,800, while the mean price of a four-door is $20,580. So I could have reached that conclusion a lot more easily and with less complexity if I wanted to. So a little side parable there on how simplicity is often a good thing. Anyway, so we have this model. What are we going to do with it? So let's say you want to make an actual prediction for a fictitious car or some new car that you've encountered. Well, it's not quite as simple as you would think it would be to get back to an actual prediction using that model, but here's how you go about it. So first of all, we're going to fabricate this new fake car that has 45,000 miles, 8 cylinders, and 4 doors. So that's what that array there means. First, we need to scale that into the same range that was used to train our model. So we're going to take that same scale instance of standard scalar that we had before and call transform on it to scale this particular car back into the same range that we used to actually train the model. And that way it will be compatible with the model that we made. We also need to insert that constant column as well again. So we're going to call numpy.insert. We're going to extract that feature data from scaled, which is what we call that resulting array of our fictitious car. We're going to say we want to insert at position 0, the number 1. Okay, that's all that's going on here. We'll then print that out, make sure that's what we expect it to be. And finally, we can call predict on our estimator that we created with that fictitious vehicle that we created and get back a predicted sale price for it. So let's go ahead and run that. There we go. So we can see that our input feature array here has that constant column 1, and our scaled feature data for the mileage number of cylinders and the number of doors. And it came back with a predicted price in this case of $27,658, which that's in the ballpark of our data. So I think that's a reasonable estimation. So there you have it. Multiple regression in action using some real data from actual car sales. A little bit, I guess it's kind of an old data set, but car prices haven't changed all that much. Not used cars anyway. As always, I encourage you to fiddle around with this further on your own. Try downloading that XLS spreadsheet from our website there. You can just use that link that was in the first block there and actually download it through your browser if you want to, and get more familiar with what's going on. So in the activity here, I suggested maybe trying to mess around with the number of doors and see if you can actually fabricate some data to make a more interesting or maybe a different influence on the number of doors on the price. And maybe you can have some fun with it and create cars that have 10 doors or something like that to try to see if you can skew things one way or the other. It would also be a good idea to take a look at the data and try to identify some of those outliers we were talking about. Try removing them and see what that does to the quality of your model. I think, like I said, there might be some supercars in there that are throwing things off for the more common kinds of cars that people generally buy. So have a little bit of fun with it and tinker if you're so inclined. And that is multiple regression in a nutshell. Again, all we're doing is doing regression on multiple features at the same time and assigning different coefficients to each feature to have a single regression model that we can use to make predictions based on more than one feature.